YouTubers, this is Roy back again. I got a couple magnetic experiments to do with you. And let's just give it a moment, let some peeps build up, and so they don't miss anything. And we'll start off with this experiment here, and I'll be right back. Who we got out there? Oh yeah, hey Tommy. Alrighty, so let's get into the conversation here. So we're going to do an experiment right now. I got this laminated bar, and we're going to put these compasses just sit on top of the PMH so they're facing the magnets. When you see the magnet with the yellow, it represents South Pole, and obviously the one in the middle would be North Pole. And obviously the compasses are reacting off of what poles we have here. So this is a cool experiment. And this experiment is going to lead into the next experiment, because we have the PMH here with copper on it. And we're coming out of the PMH here into an analog meter, which will move to the positive and negative. We also have an oscilloscope hooked up here, and we're coming out of the PMH into the analog meter, coming out of the PMH into a voltage multiplier. I'm only multiplying it one time, step the voltage up. We're coming out of the voltage multiplier into this What's going on, Tommy? Dave? We're coming out of the voltage multiplier into this digital meter, and take a note that it takes 3 volts for it to turn on, and that would be coming from the PMH. And then I have this Model T Ford Buzz box. It was where the high voltage came from, or it was made to supply to the spark plug. And in true fashion of what I do is I love to take stuff apart and see how it works. This actually had a little issue, so I took it apart, and there you have there was a break in the insulation around it. So we'll go back over here, and so here we are with south, and that's representing South Pole, North Pole. So the experiment here is we're going to turn the wheel slowly, and you'll see the compass turning. At some point, as the wheel gets faster, there's a magnetic saturation, I noticed. And you'll see that with our eyeballs when the compass wheels are no longer turning, but they fixate themselves in a direction. And that got me curious. So that's why the laminated bar, we're going to look at positioning. We're going to be doing multiple tests here, at least 4 with this. And this one is, we're going to turn the wheel, this would be counterclockwise, and this is clockwise. So we'll start off with clockwise, and we'll do it without the bar. And then we'll go ahead and put the bar down, and we'll see the difference. So let's go ahead and we'll start spinning this slow. See, the wheel's still turning. You know, they're starting to react a little bit because the wheels turn a little faster. And remember, I'm turning this by hand. Now I'll just get it going, right? And get it humming. And look at the positioning. There's your North Pole with the white. There's your North Pole with your the left there. Hi all, Tommy Tom in the house. Turn them wheels, guys. Get this knowledge out there. So basically you can see that they're both heading out. So the souths are facing each other, right? So we're turning this clockwise without the core, without the laminate. Let's go ahead and slow this bear down. Remove the compasses. We're going to put laminated bar across. Now, this now becomes a keeper bar. So now it allows the flow in through iron. So now watch. Go with same position, clockwise. You can see we have movement again. And notice this. Notice a lot of stuff. So notice which way the wheels are turning. And keep an eye on your norths and positioning. So here's your south, facing your south. Here's your south, it's facing the south, and there's your north facing the north. And then, and this is, remember, this is happening to the iron bar. So now we're going to get in the middle. And what happens? The souths are towards each other, which would be because this is now in the middle, so it's pulling the compasses. And then now you have your south over here and your north over here. So let's go ahead and move this now and look to see if it's similar to what it was before. Let's get this thing moving there. now there's a difference. Now you can see they're both facing inward, north now. Let's slow this thing down. All right, remember all these positionings because there's going to be 4 of these for you guys. And you can go back to the video later to check it out, but you're going to see a difference. Why am I taking them off? And now we're going to turn the wheel the opposite way. All right, now we're going to go counterclockwise. Let's see if there's any difference from what we've just seen. We've just seen that the norths were facing inward, right? So the same turning. Yeah, right. Strange. Slow the wheel down. Let's take these off. Take off the kicker bar. Now, we do the same. We're facing in, right? Now the keeper bar's off. So now they're facing this way. And if we slow this down, and if we could turn the opposite way, facing away from each other. Very important. Very important. Let's move on to the other side of the table. So now we're going to get into the PMH. Like I said, it's hooked up to this analog meter. Let me stop. We have the oscilloscope too. Heartbeat. All right, so here's your analog meter. And the reason we start off with that test, because I'm trying to show you guys something that I noticed, and it seems to be very important in some of the experiments that I've done in the past that now kind of make sense, which is we're going to see that right here, this isn't an analog meter where it has a split in the middle, where the negative is that way and the positive is that way, but it stops there on its own. So we're going to say that when it's buried, it's at the negative point, at the valley, and when it's up, it's at its peak. So what I've noticed here is that it only peaks when the same magnet is approaching the same pole. The same poles are approaching each other is when it pushes away. It empties out into the coils. The timing of how it does it, it never occurred to me. So to me now, it is very important to know that the magnetic field in front of each other, or should I, yeah, because when this is reacting off the iron, it's creating a magnetic field, so it's opposing each other. Then it's getting pushed out, and it goes into the analog. We're going to see a couple things. We'll go to one example at a time because I'm kind of excited about it. And then it's also going into this digital meter, which takes 3 volts for it to even go on, which is coming solely from the PMH. And then I'm coming out of the PMH and going into a voltage multiplier just one time. And then that is going into the digital meter to build it up, because I couldn't get it to turn on just by itself. I would be able to, I guess, if I was coming out of it with a full wave bridge rectifier, but I didn't even go that route because I like the voltage multiplier. So right now, the south is on the north, and we're not turning the wheel yet, but you're going to see that it pulls down. See how see it pulling down? It's pulling down. So that's, right now you got south and north. You got two opposites right there. So they're charging the iron core right now. So the iron core right now is at its saturated point. And now we're going to go ahead and pull away from it. And you can see that's where it just keeps going down in the valley. It's going down in the valley. So basically what's happening is the iron core right there that was saturated starts heading the hell back out. And because this is getting pulled away, there's going to be a snapback. And right now, watch it get pulled down. And look, we already passed it. It never came up. Well, it did right now because I just moved the wheel a different way. See how I'm moving it? But let's go back to it. So basically, we're at north-south. It's pulling down, pulling down. Look at the wheel. The wheel still past this halfway point and going on to the next magnet. So basically, it didn't do anything but went down. So it went down as a negative. Now, all of a sudden, you go past that, you have now a south and a south. And right now, when you pull out of that, that thing rises. Look how it rises up. So it takes the same poles to push out the coil, the electrons through the coil. Let's go ahead and move it slow. And the other part of this is, the reason we did the first part of this video is the saturation in the magnetic field, where these can no longer turn. They just start directing themselves. Why? I'm still questioning it, but I would think that there becomes a neutral there or of some sort, and they're adjusting themselves to the magnetic field of the planet. But sometimes they do different things. So here you can see we're going slow, and as we go faster, you're going to see this needle not climb no more. So there's a frequency, a speed of frequency that inherently is causing your peaks, which we'll get into the oscilloscope next, which is, we will visually see it, but here we're seeing it in a analog form. So, and I explained to you what's causing the peak, where the same poles are together pushing out through the coil. So let's go ahead, and once I get to a certain speed, this meter is no longer going to jump all the way to the very end, because it's hitting the very end, so it wants to keep going. It'll hover over here, and that's because there's going to be a saturation. You guys watch the wheel. Look at the meter. Now you can also see the voltmeter in the front go on. You can get a little speed going here. All right, it's by hand. So now you can see we're almost burying it down the negative. So think about what I just said. Very important that the negative is being presented and it's pushing, because it's constantly pushing. It's pushing. It's pushing, pushing, pushing. There's your volts. All right, let's go to the third part of this. Let's go ahead and slow this thing down. Now we're going to go into the oscilloscope. All right, so right now there's nothing turning. Now remember, this is coming out of the PMH, going into this sucker, and this is going to show exactly what the digital was showing, the peaks and the valleys. Now, we're going to include something else into this visual part when we turn the wheel. Not only are we going to see the peaks and valleys, we're going to analyze the top of the peak, and to have a perfect smooth peak, you don't want to see any points in there. And we're going to go ahead and see if there's points. If there is, we're going to go ahead and try to adjust the points and see if we can round off the tops of the peaks. Very important. So let's go ahead, and now we're Starting to turn the wheel. You can see the digital meter. Well, you can see the analog meter and the digital. It'll start to turn on. So it takes 3 volts for the digital to turn on. You can look at the analog meter. Now look at the oscilloscope. Now, something I want you to see, I got it turning, just by hand. Look at the peaks. You can see there's a point up top. Now let's go ahead. You don't want that. You guys see that? At the peaks, looks like Gumby. Now that is an unbalanced AC wave. Unbalanced. The way to balance that is we're going to stick a capacitor. Let's see, where do I have? I got another lead here. And it's shaking pretty good over there. Give me a second, guys. We're going to, well, maybe I stole the wire. All right, so we'll take this wire, and then we're going to come out. Well, that's that analog slamming. Look at that. Wheel slowed down. You get more power. So that's another thing I want to explain to you guys is, too much speed with this, you start to lose your oomph, your base, we'll call it, your current, pretty much. I need a jumper cable. Let's go get one over here. Jumper. And this is pretty cool too, because now we can smooth that line out by adding a capacitor in line with this in the circuit. Now that, and that's on the wire. Sorry about that. I think I picked a bad alligator clutch. Not that good, but see if it still works. So now we'll go ahead and we'll get this wheel turning. And now we're going to look at the peak now. And we'll see that we smooth it out a little bit. Now this is, we can change, I'm sure, change the capacitor that we have. We're using an electrolytic capacitor. But you can see we smooth the tops out. We're not having them strong peaks. That's really good. Really good. Now we're over to the buzz box. Now remember, this is pushing when the same pole here is on the same pole there, and it's pushing out. Now you can see your peaks are all rounded out. Now let's go ahead and, for instance, let me just get a little bit more spin, right? Just to keep it. Now you look at your peaks. I'm going to disconnect the capacitor, okay? So disconnect. And now look at the top. They turn to Gumby. And disconnect it right here. And you come back over here to capacitor. Now if you change your capacitors, you can smooth it out even better. Now we'll come over to the buzz box, and you can see that I have a spark gap here, a little gas tube buzz box, and let's go ahead and make the connection. She rolls. She rolls. Got going. Well, seems like it took a dump on me, guys. I don't know why it's not working. Not supposed to be like this. Well, looks like I'm not going to be able to figure this one out right now. Some reason. Not going to do it for us. Oh, spark gap lights up off of the impulsion over here. And pretty cool shit, especially if you're getting into radio, because it's perfect for sending radio signals. So you can send the radio signal out of this into your coil, into your waves you want to create, and it's all coming from Ed's wheel, especially going out to a tripod. So leave your comments. See if I can't show you that. And that spark gap, man, it just lights up all purple, looking beautiful. I don't know what's going on. Digital's getting some telegraph there. Shit, this thing should be working right now. Well, guess that's why. Hold on, let's shock here. No joke getting shocked by this sucker. Not cooperating. I apologize. Don't get to see the purple. All right, guys. Well, anyway, thanks for watching. Leave your comments. Ever since I put that wheel bearing on a thrust bearing, it's remarkable. Very little resistance.